Good morning, students. In the last class, we have just discussed about a few problems associated with application of Gauss law. And one of the problems that was discussed is this one. Uniformly charged conducting sphere has volume, charge density rho, and material is removed from the sphere leaving a spherical cavity so that the electric field through the cavity is uniform and is given by where A is the distance of the center of the two sphere. Now, all these were discussed in the last class. In this case, we just treat the two sphere as a separate identity or entity. And we take charge density of those sphere which is removed from the initial charged sphere as negative, so minus rho. And those which was initially charged is taken as plus rho. Then we find out electric field due to each sphere. And after that, we apply superposition principle to calculate net electric field. So look at here. Here is the result. So a thin conducting uniformly charged spherical cell of radius r, this is another problem, has total charge of Q over it, and a small circular plug is removed from the surface, just like this. Say a small circular hole is made on the surface. What is the magnitude and direction of electric field at the center of whole sphere? Now try to understand. And one more thing, what is the magnitude and direction of electric field at the center of this hole, circular hole, and at the center of this sphere? The plug is put back in the hole. Using the result of part, calculate the force acting on the plug. You know that the situation here, replace the spherical cell with hole, with a perfect spherical cell and a circular disc like with equal negative surface charge density. So those part of the cell which is to be removed take with negative surface charge density, and those which is the initial sphere taken as positive charge density, but charge density will remain equal and opposite. Again, then we find out electric field due to this whole sphere, and then we find out electric field due to circular disc that is removed from the cell, and then apply principle of superposition to calculate net electric field. After this one, you must try, because this is very important problems that you might not have in your textbook or in any other refresher book. So just note down. Now, in order to calculate force, remember, once again, come back here. We have to plug is put back in the hole. Now, whatever the part removed is brought back to the hole. So using the result of part A that you have got in the part A, calculate the force acting on the plug. So remember, when this part was removed, then net electric field at this point was non-zero. So when that charged circle or circular disk is brought near this non-zero electric field repel that one. So electric force is equal to electric field and into charge on that circular disk. And so we have here dF equal to dq into E. E is the electric field at this hole due to whole sphere. Now, and dq is the small amount of charge on this circular disk that was removed. So in order to determine the charge on this circular disk, just you multiply the area of this disk into surface charge density sigma. So right now we treat, because area is not known, so just we take it as dq as the charge on this disk. So we have electric field equal to electric force equal to capital Q, that is total charge on this disk, into dq, and that is equal to 8 pi epsilon naught r square into V. This is unit vector r, radially outwards. So electrostatic pressure, that is force per unit area, tending to expand the sphere, just as you blow air into the balloon expand in the same way, because this force is acting outwards. So it tends to expand the sphere, but a sphere is a solid and conducting, therefore it does not expand. But to what extent it can withstand that pressure. So remember here, first of all, we have calculated force, and then we have to calculate pressure. So when force is divided by area, that becomes pressure. So when you divide area dA, because charge on this one is dq and area of this one is dA, so dq upon dA equal to sigma, surface charge density. So then it becomes q into sigma 4 pi epsilon naught r square into this much. Now, this becomes 32 pi r square epsilon naught square r to the power 4 this. And now try to understand how it became so. So here formula is q into sigma 8 4 pi epsilon naught into r square. Now we have to calculate numerical value of sigma and put it here. Then you will get this result. How will you calculate the sigma? You know well that sigma is surface charge density, is a total charge on the surface of the cell divided by surface area of the cells. So total charge on the surface of the cell is Q in the question given here. Total charge on the surface is Q. And total surface area of the cell is, with radius r, is 4 pi r square. So divide Q by 4 pi r square, that becomes total charge per unit area, and this indicates that surface charge density sigma. So here value of sigma is Q upon 4 pi r square. So you place here Q, so Q into Q becomes Q square, and 8 pi epsilon naught r square into 4 pi r square. So 8 pi into 4 pi equal to 32 pi square epsilon naught into r square, r to the power 4. So this is the result. Try to understand the things to be remembered here. Here epsilon naught square involved. As before, we have discussed that sigma is just equal to Q upon 4 pi epsilon naught. Not epsilon naught, 4 pi r square. Q upon 4 pi r square. So when you place here Q upon 4 pi r square, epsilon naught does not involve in the expression. Therefore, here a square of epsilon naught must not be there. only single epsilon naught must be there. So q square upon 32 pi square epsilon naught r to the power 4. And this is a radius vector. So here, this is the pressure. And here, pressure is, we know that a scalar quantity. But here, in order to indicate the direction, pressure will be in which directions? It will be outwards. Therefore, radially outwards. Therefore, this unit vector r cap is given there. So this was the one of the important problem. Now, try to understand another example. Find electric field outside an infinite non-conducting plate of charge with uniform charge density sigma. Remember, in your textbook problem, there must be electric using Gauss law determine electric field due to infinite thin charge sheet. The same problem is here. Only language has a little bit different. So find electric field outside an infinite non-conducting plane of charge with uniform charge in TC sigma. So only word has been not discussed here, the thin charge sheet, infinite thin charge sheet. So let us consider, because it is a case of thin charge sheet, because area of both sides is taken to be important. Uh, so first of all, say this plane act as a thin charge sheet which is infinitely extended in this direction up to infinity and extended in this direction up to infinity. So say this is y-axis and this is x-axis, then this plane is xy plane. So x-axis extend up to infinity and y-axis extend up to infinity. So this plane sheet act as an infinite sheet and of charge density sigma. That means charge given onto this surface, infinite sheet surface, which is uniformly distributed over the surface. Therefore, surface charge density is denoted by sigma. Now, in order to calculate electric field at this point, say at this point or at this point outside the sheet, in order to that, we take pills straddling the surface. So here concept of fields has been taken because no surface is there that will enclose this infinite sheets of charge symmetrically. So here we cannot take any spherical cells or cylindrical cells or cubical cells because no one will enclose it symmetrically. So we take a pills, concept of pills. We take a small cylinder with a small surface area dA. This is the dA and dA. And at this point, we have just discussed that just you draw the charge distribution and then indicates the direction of electric field. And after that, find out the flux linked with the Gaussian surface. And after that, put that flux in the Gauss law equation. So here, our Gaussian surface is pills-like. This is a cylinder, say it is a certain distance away from the sheets, and electric field is perpendicular to these sheets here. And on the curved surface of the pills, electric field makes an angle of 90 degrees with the curved surface. So flux through this curved surface is 0. So we don't need to calculate this. But flux through this surface, because area vector will be directed in this direction and electric field is also in this direction. So here flux will be positive. Now, similarly at this location, because seat is thin, so thin concept of thin sheet means that the charge appears on this side, the same charge will appear on this side. So we have to take flux through the surface on either sides, and then we find out net flux. So take advantage of the symmetry property we use as our Gaussian surface, a cylinder with axis. uh, with axis perpendicular to the sheets of charge with inch of the surface area S, or we can say dA or ds. The charged sheet pass through the middle of the cylinder's length. So the cylinder ends are equivalent from the sheets. Therefore, this ends and this ends are equivalent because sheets passing through the cylinder at the middle of the length of the cylinder. So first of all, we have to find out flux through this end, that is E dot dA, as we know, and similarly through this end E dot dA. This is left bottom, and this is a side. A side is this one. So left bottom, and this is right bottom. So due to side, because lateral curved surface area of the cylinder makes an angle of 90 degree with the electric field. This is electric field, and this is area vector directed in this direction. So far we have discussed that when you put a normal to the surface of the area, that area becomes vector. So here these two vectors makes an angle of 90 degree. Therefore, electric flux is just equal to dot product of electric field vector and area vector. And here, if angle between two vectors is 90 degree, their dot product will be 0. So this case is 0. Now come to this point. Electric flux through this surface. Area vector and electric field both are parallel to each other. Therefore, angle between them is 0. So a scalar product will be maximum. In that case, E into S flux through this surface. And similarly, E into S flux through this surface. And now add up all, we get 2ES. This is net flux. So we have calculated net flux through the Gaussian pills that we say a cylinder due to this charge sheet. After that, what we have to do, we have to equate this flux with the total charge enclosed by the pills divided by epsilon naught, as Gauss law say. That net flux through a curve, net flux through a surface enclosing the area, certain amount of charge is just equal to 1 by epsilon naught times the charge enclosed by the surface. So here total flux is 2 into E into S. Now we have to look over how much charge enclosed by these pills. So area of these pills is S, and surface charge density is sigma. So charge enclosed by this surface equal to area of this surface into surface charge density. That is S into sigma equal to Q. So we have calculated amount of charge enclosed by these pills. So Q equal to S into sigma. Now put this value in Gauss law equation. That is total flux E dot dA integral equal to Q by epsilon naught, and put the value of Q equal to sigma into S, and now put the value of this one is equal to 2ES, because after integrating all these things we have got this one. So 2ES equal to sigma into S. SS will get cancelled out. So E equal to, that is electric field, equal to sigma upon 2 epsilon naught. That will be the result. Sigma upon 2 epsilon naught. Okay, so next thing is that we have to remember, I think all of you would have understood well. Now try to understand this graph. So if you take x-axis as the axis of this cylinder, then you will see that as we move away from the seats, electric field remain constant, because in the expression electric field equal to sigma upon 2 epsilon naught, distance does not involve. So it means electric field due to infinite thin sheets is independent of distance or position of the point where electric field is to be determined. So this remains constant because sheet is infinite. So when you move away and away and away, still electric field remains same. That its magnitude only will depend on surface charge density sigma. It is directly proportional to surface charge density sigma, and it will also depend between medium or different medium between the points and seats. If it is if it is sorry, vacuum, if it is vacuum, then we write epsilon naught. If it is some any other medium, then in place of epsilon naught, we write here epsilon. That is electrical permittivity of a medium. Next, this is also a problem. Nowhere inside between the plane, an odd number of parallel planes of the same non-zero charge density is the electric field zero. So try to understand. Nowhere inside between the planes. If we take two planes, sheets of charge, plane sheets of charge, say it is infinitely extended sheets, then at any point in between the two parallel plates, electric field will be zero. Is it right or wrong? Answer would come, yes, it is right. You will try your best. So let me discuss here. This is the two parallel plates. Say this is one parallel plate and this is another parallel plate, and both are parallel to one another, separated from one another by certain distance. Now say if plate 1 has charge density sigma 1 and plate 2 has charge density sigma 2, then we have to find out electric field due to this configuration of charge sheet at a point on this side, at a point in between the two plates, and at a point right side of the two plates, at a point left side of the two plates. So electric field at any point at the left side of the two plate will be vector sum of electric field due to first plate and due to second plate, because this plate is infinite charge sheet. Therefore, electric field due to plate is independent of distance between the points and plates, between the points where electric field is to be determined and plates. It will only depend on charge density, surface charge density. Therefore, first of all, we have to find out electric field at the left of the two parallel plate. So first we find electric field due to first plate is given as sigma 1 upon 2 epsilon naught into I cap. I cap indicates that electric field will be directed in the direction along x-axis. So if we move and left side, the unit vector I cap will be negative, and if we are in this direction, electric field unit vector I cap will be positive. So here, electric field E1 will be equal to sigma 1 upon 2 epsilon naught into minus I cap. Okay. Now at the same point, we find out electric field due to second plate. So at the same time, electric field due to second plate will be sigma 2 divided by 2 epsilon naught into minus I cap, because both the electric field due to both the plate will be in the same direction towards the left side or negative x-axis. So in that case, taking minus common, we have result minus 1 by 2 epsilon naught into sigma 1 plus sigma 2. So this is the electric field at the left side of the two parallel plates. Now we come to this point in the region. Say at the mid of the two plates, let there be a point P at the mid of the two plates where electric field is to be determined. So again we take, find out electric field due to individual plates, and then we find out vector sum of the electric field due to these two plates according to superposition principle. So first of all, we find out electric field due to first plate. So at this point, say at this point, electric field due to first plate will be directed along the positive x-axis, that is in this direction. Therefore, electric field due to this plate at this point will be given as E1 equal to sigma upon 2 epsilon naught plus I cap into plus I cap, or sigma upon 2 epsilon naught I cap, positive. Now, same at the same point, electric field due to this plate will be sigma 2 divided by 2 epsilon naught into minus I cap, because this point will be left of this plate and this point will be right of this plate. So direction of electric field due to these two will get changed out. As direction is opposite to each other, now we have calculated electric field due to individual plate at the same point between the two plates. Now we have to apply superposition principle, that is vector sum of the electric field due to each plate is just equal to net electric field due to parallel plate in between the two plates, at a point in between the two plates, which is given as 1 by 2 epsilon naught bracket sigma 1 minus sigma 2 into I cap. So next thing is that we have to calculate electric field at a point on the right side of the two parallel plate here. So we say this is the third region, this is second region, this is first region. This is first zone, second zone, third zone. So at the three locations we have found electric fields. So electric field at this location will be negative and electric field at this location will be positive. Only difference is that their direction will be opposite to one another, because if you take here as a single point P where electric field is to be determined. So electric field due to first charge plate is determined as sigma 1 upon 2 epsilon naught I cap. And electric field due to second plate is also given as sigma 2 upon 2 epsilon naught I cap. Here in both the case I cap is positive because point lie on the right side of the plate 1 and plate 2. Therefore, electric field due to both the plate will be in the same direction, so add up. And right side along the positive x-axis, that's why it is positive. So we write here electric field in third region is equal to sigma 1 sigma 2 divided by 2 epsilon naught into I cap. So electric field, net electric field in the third region is just opposite of that of the first region. And magnitude in the first region and third region will remain same. And lowest electric field is obtained in between the two plates, because here we see the difference between the two. Now, is there any mechanism that we will have zero electric field at this region and zero electric field at this region and maximum electric field or non-zero electric field at this region? Is there any mechanism? Yes, of course. If you put equal and opposite charge density over the two plates, you will see that electric field on either side of the plates will become zero, but electric field in between the plates will be non-zero and is equal to sigma upon 2 epsilon naught. So let us discuss. Let me just you will try your best. First case you have to try. Take it as homework, or you will do it on your own. This was the case. Now you have to generalize the case. This is the generalized case. Now, where charge density on the first plate is positive and is same plus sigma 1, and charge density on the second plate is negative, say minus sigma 2, then what will be the result? What will be the three case you have to calculate? Next. Now, if equal charge is there, equal charge density is there, say here is sigma 1 equal to sigma and sigma 2 is also equal to sigma, then what will happen? then you place here sigma and you place here sigma, then sigma plus sigma equal to what? Minus 2 sigma divided by epsilon 2 epsilon naught into I. So 2 will get cancel out. So we get results minus sigma upon epsilon naught. And in this case, sigma equal to sigma 2, sigma 1 equal to sigma 2. So electric field will be 0. In this case, in between the two plates, electric field will be 0. And on the either side, electric field will be non-zero. Here sigma 1 equal to sigma and sigma 2 equal to sigma. So sigma plus sigma 2 sigma, that is equal to sigma upon epsilon naught into I cap. So on the left side, electric field will be minus sigma upon epsilon naught into I cap. And on the right side of the parallel plate will be plus sigma upon epsilon naught I cap. But in between the two plates, it will be 0. Now we have to obtain reverse case. So here is non-zero and here has to be 0. Electric field has to be 0. So for that one, we put plus equal and opposite charge density over the two plates. Here say plus sigma and here say minus sigma. Then you plate, if you place this at that one, then you will get here plus sigma minus sigma will get 0. So electric field will be 0. And here plus sigma minus sigma equal to minus plus. So sigma plus sigma 2 sigma, that is 2 sigma upon epsilon naught, 2 epsilon naught into I cap. So 2 cancel out. So sigma upon epsilon. So in this case, in between the two plates, electric field will be sigma upon epsilon naught I cap directed along this direction. Now come to the point. At this point, again, sigma 1 equal to sigma and sigma 2 equal to minus sigma. So sum of this one becomes 0. So electric field will be 0. So in this case, electric field in first region, electric field in third region is 0, and in between the plate is not 0. So we have got 3 cases in this case. So you have to practice. Now, next problem is that find electric field of a slab of non-conducting material forming an infinite plane. Now, in the previous case, it was the thick sheet. Now here it is slab, not thick, not thin, it is thick. And in previous case, it was thin. So in case of thin sheets, we take same charge on the either side of the sheets, but in case of thick, we cannot take same charge on either sides of the slab. So say this is a slab which has thickness D and carry a uniform positive charge density over it. In this case, what will be electric field? And all the things are similar to that in previous case. This slab is infinitely extended, infinite plane of slab or thick sheet. So what will be electric field at a point outside the this thick sheet? So here we have to remember, in this case, we don't need to find out flux due to this side and this side. While you are considering the flux at this side, then flux inside will be non-zero. Flux inside will be 0 if it is conductor. And if it is non-conducting material, then flux will also be there inside the thick sheet. But this flux and this flux may not be equal. So first of all, we have to draw. Everything will remain same that we have discussed in the previous class, that total flux through the surface is equal to 2 into ES. Now, say here volumetric charge density is to be considered because it is thick sheet. So charge will be distributed throughout the volume of the slab. Therefore, we have to consider volumetric charge density. So volumetric charge density, rho into surface area into D. This becomes volume. Area into distance, height becomes volume. So this is the volume of these pills. So how much charge enclosed by this volume, that will be equal to rho into S into T. SS will be cancelled out. So electric field will be rho into D divided by 2 epsilon naught. Now try to understand, this is the electric field outside the slab. This is the expression for electric field outside the slab. And now we have to, and one more thing we have to discuss here. If distance D, that is separation between the two face of the slab, is much more smaller, then this slab can be treated as a thin sheet. But right now we cannot treat it as a thin sheet. If D tends to be 0, then sheet becomes thin. In that case, rho will be replaced by sigma, and your electric field will be sigma upon 2 epsilon. So right now we have to calculate. We have calculated electric field due to a thick slab, charged, non-conducting slab, and which is infinite plane, is rho into D upon 2 epsilon naught. That means electric field outside the slab depends on thickness of slab and charge density of the slab. More is the thickness, more will be electric field. Now come to the point inside. When we come inside, then inside the slab, we have to take a Gaussian surface, just like pills. So this is a cylinder. So same formula has to be applied here. Total electric flux through this surface, this side and this side, is 2 into E into S equal to rho S into 2x. So try to understand, this is the center, a line passing mid of the thickness of the slab. So, and say this Gaussian surface is separated by a distance x from this line, and this is separated by x from this line. So this is minus x and this is plus x. So separation between two is x minus x equal to 2x. So here we write volume of this cylinder is equal to 2x into S, equal to volume. And volume into volumetric charge density equal to total charge enclosed by the surface. So we get here rho into S into 2x, SS will get cancelled out, 2 will get cancelled out. So electric flux will be rho x upon epsilon naught. Sorry, electric field inside will be rho x upon epsilon. So when x becomes 0, that means when you come exactly at a point between the two face of the slab, then electric field will be 0 at this place, because x becomes 0 at this place. But as you move away from the center of the midpoint of the thickness of the slab, then electric field go on increasing and becomes maximum at the surface and becomes equal to this one. This is very important cases. And now try to, if you plot the graph between distance and electric field, you see that at the center of the thickness of the slab, electric field is 0. As you move, then electric field increases and increases and then becomes maximum, and that maximum value is rho D upon 2 epsilon naught, because at that time x becomes equal to D. Now, as soon as we comes out of the space of the slab, then electric field becomes constant and independent of distance, because slab is in finite plane. So this will remain same. So this graph becomes like this. It's okay. I hope that all of you would have understood well, and you will practice it more and more. I will upload the same lecture on the YouTube. You will review it again and again. Then concept will be clear. Now, the question is that differential form of Gauss law, that we don't have to study in this section. You will study all those things in engineering section when you join electrical engineering, and then you will study all the things. These are the Laplacian operator. And now come to the point. one of this is also of a higher level, so you don't need to discuss about this. Now, this is the summary of the chapter.